This is the hardware and software session, so I think it's about time we redress the balance. So I'm the director of quantum applications at PsiQuantum. If you attended our keynote yesterday, you'll probably be more familiar with PsiQuantum as a hardware company. Largely speaking, the majority of the employees at PsiQuantum are singularly focused on delivering large-scale photonic quantum hardware. But of course, we also have a vested interest in building useful and commercially relevant applications for that hardware. And so, in fact, I lead a team of 20 people at PsiQuantum, all of them quantum application developers, who are singularly focused on, well, in generality, building quantum algorithms and quantum applications for large-scale fault-tolerant quantum computers. But more specifically in designing quantum algorithms for the kinds of devices that PsiQuantum is planning to build. So that is closely incorporating algorithm development with the architecture and the hardware that sits underneath. Now, one of the things that folks outside of quantum application development say to me most often, and it's been said to me 2 or 3 times this week, is that there aren't enough of you. There aren't enough quantum application developers, and you aren't developing quantum applications at a fast enough rate. And I share both of those sentiments, but to some extent, I want to convince you in this session that this is a problem that is partially of our own making. And so the goal for the next 20 minutes is for me to tell you what I believe one of the key problems are in developing quantum applications today and how we go about fixing it. Before we get there, though, just a little bit of a preamble. So maybe this slide is less relevant for this iteration of Q2B, but many years ago, PsiQuantum was pretty contrarian in claiming that large-scale error-corrected quantum computers were necessary to deliver meaningful, commercially useful applications. That is now no longer the case. That's an opinion that's shared by a large number of other players in the space, both in academia and in the private sector, and across hardware vendors, folks that are writing quantum software, and also entities that will ultimately be end users of quantum computers themselves. However, there's obviously a gulf in capabilities between the machines that we have access to today and the kind of devices that we need to build in order to derive commercial advantage. So the majority of the roadmaps of the entities that you see on this slide that have been publicly disclosed aim for devices with millions of qubits of a sufficient quality to be below the error correction threshold for whatever error correcting code they plan on implementing. But despite this gulf in capabilities, I'm sure every hardware vendor that has given a talk over the last few days has told you, very explicitly that they have lots of plans for scale, and all the problems that they face with scalability are all going to be magically solved, and they'll get there within this decade. And in fact, we've seen many of those talks throughout the week. And guess what? PsiQuantum is no different in that regard. But it's worth saying that for fault tolerance to arrive that quickly, we don't all need to be right. It's not the case that every single entity on that previous slide needs to execute faithfully on their roadmap for the fault-tolerant era to begin. Everyone else could fail, bar one company, and the fault-tolerant era would still be upon us. Okay, so that's just something about the scale of hardware. The good news is that we are increasingly confident in our ability to run useful applications on machines of that scale. So this is just a plot of a smattering of quantum algorithms that have been explicitly compiled as a function of time, plotted against the computational volume. And I want to be very clear here. The y-axis here is not the IBM coined notion of quantum volume. By volume here, I just mean the product of the number of logical qubits with the number of logical operations, in this case, the number of Toffoli gates, plotted as a function of time. And there are 2 things that I want to highlight from this plot. One is that, unlike NISQ, I can be very explicit about resource estimates for algorithms, even in advance of the hardware being here. So they lack the heuristic nature that you might expect from NISQ algorithms. I can put a very specific dot on this plot with a very minimal error bar and be very confident about the resources needed to run a particular algorithm. The other thing to say is that resource counts for algorithms have dropped significantly as a function of time, often by very significant amounts. I've been at PsiQuantum for just over 4 years. The field has faithfully dropped common benchmark algorithms like finding the ground state energy of Fumoko or solving elliptic curve cryptography by an order of magnitude a year for the last 6 or 7 years. However, that previous slide does belie the difficulty in deriving resource estimates for these problems. So going from a broad computational statement through to an explicitly specified quantum algorithm, compiled all the way down to low-level instructions, and then the tedious bookkeeping of doing the resource estimation itself. And we are not immune from this. This is pain that we equally share. So this is a paper that we published in March this year. It was a paper specifically that was aiming to compute a variety of molecular observables for essentially arbitrary quantum chemical systems that we co-published with our friends at Boehringer Ingelheim and QCWare. And it's worth noting that in building this algorithm, the high-level structure of the algorithm itself was known about 3 weeks into a year-long collaboration. The difficulty in deriving results like this really isn't in deriving high-level structure of these algorithms. It's in the fastidiousness that you need to take that high-level algorithm and to break it down into low-level primitives that are amenable to resource estimation. And then the meticulous process of doing all of the tedious bookkeeping that you need to resource estimate these algorithms by hand. And that consumes 95% of the time needed to generate results like this. The data on the right-hand side does demonstrate the output of this work, and you can see that there are resource estimates for a variety of molecular systems and a variety of observables in a variety of different basis sets. But it's, I can't stress enough how painful it is to produce data that is of this caliber. And this is generic across the field, right? So if you want to take a broad computational statement and push it all the way through to an explicit statement of resource estimation, the workflow looks something like this. So it takes of the order of weeks to refine that computational problem, to marry it to a quantum algorithm specified at a high level. It might take a month or two to instantiate that thing, either with a sufficient level of theory or in code. And then it'll take months or weeks, 2 or 3 of each, to compile that thing to low-level primitives, to carry out the resource estimation, and then to invoke some kind of optimization if the numbers are too big. And if you believe that fault-tolerant quantum computers will be here within the decade, at this rate, this gives us half a dozen cycles at most to derive meaningful applications for these machines. And clearly, we're not moving quickly enough. The second thing to say is that we are still, for better or worse, in a world where 95% of quantum application developers are building NISQ algorithms. And there's often a misapprehension lying under the surface here, which is that a fault-tolerant quantum computer is just a larger or more capable version of a NISQ device, much in the same way that this old Intel microprocessor is just a slower, less capable version of its modern-day counterpart. But that's not the comparison you should make. The comparison you should make is this. It's an old Intel microprocessor versus a high-performance supercomputer. And I don't think anyone in this room would contend that the Frontier supercomputer is just a larger, more capable version of the microprocessor on the left. At some point, the difference in scale and the difference in capabilities is so significant that it necessitates new infrastructure, new architectures, and entirely new ways of designing applications and software. And I should highlight that that is emphatically the case when we are designing fault-tolerant quantum algorithms. So this is an unpacked schematic of the structure of the algorithm, the chemistry algorithm that we saw a few slides ago. And you can see that it has a fairly complex nested structure. So it's invoking quantum phase estimation twice in 2 very different ways. That inner phase estimation is itself invoking quantum signal processing. That quantum signal processing is itself invoking some novel qubitization, et cetera, et cetera. And not only is the entirety of this algorithm not suitable for running on a device where you have a limited number of qubits and a limited amount of coherence, even the constituent subroutines of this algorithm are not suitable for devices with limited number of qubits and a limited amount of coherence. And the upshot of this is that fault-tolerant algorithm developers are largely developing algorithms that are totally alien to people that are working on NISQ. And moreover, expertise and accrued experience in building NISQ algorithms is largely tangential to the kinds of expertise and experience that you need in building fault-tolerant algorithms. Okay. Luckily, there are some solutions to these problems, and they don't necessarily predicate a PhD in quantum computing to understand. So I've highlighted 3 just with the brackets at the bottom of this slide, so let's step through them. On down-selecting algorithms, the main problem, I think, is reusability. So it's very difficult to take the algorithm as specified on the previous slide, or indeed, if you just pull the paper from the archive, and repurpose it for a slightly different task, or substitute out constituent subroutines for a new variant if you come up with something that is better or more optimized. And instead, this fault-tolerant algorithm development often requires algorithm developers to start entirely from scratch, or it requires them to carry around the entirety of the literature on the compilation of quantum algorithms in their head. And what we would rather have is a general-purpose, ubiquitous library of pre-compiled subroutines that algorithm designers can reasonably pull upon, written in such a way that you can deploy them modularly, much in the same way that you could deploy them in this nested structure in the algorithm that we saw on the previous slide. On instantiation and compilation, the primary driver to accelerating this process is to specify high-level languages for quantum algorithms. And so, specifying languages for quantum algorithms at a high level and abstracting away low-level compilation details frees up a lot of time that application developers would have been spent bookkeeping low-level details of quantum algorithms, and allows them to iterate much more quickly on high-level designs of quantum algorithms. It means they get to valid and optimal algorithms significantly faster. And lastly, having those automated compilation tools makes resource estimation a push-button exercise. And if we can appropriately cache and store those compiled algorithms in a modular fashion, then anytime we come up with a new variant of a subroutine that we think is better than what we currently have, we can substitute that into the algorithms that we have built into our library and provide updated resource estimates across the board. And in fact, I'm going to give you a flavor of some of PsiQuantum's progress on these 3 points in the next few slides. Okay, so on building a library of use cases for quantum algorithms and quantum applications, we've taken a dual approach. So on the theory side, we've pushed towards building out the breadth of ubiquitous quantum algorithms that previously had only a big O attached and now have an explicitly compiled version where we can tease out all the constant factors and understand exactly how they compile. But on the software side, we've built out a fairly easy-to-use software framework that allows us to readily implement these algorithms in code. So we'll talk about the former on the next slide, but on the latter, you'll see here a snapshot of the set of computational primitives that we can already invoke. And it's now fairly extensive and robust as a toolset with respect to modern quantum computational primitives. So there's alias sampling and various flavors of amplitude amplification and LCU and qubitization methods and signal processing further down, et cetera, et cetera, et cetera. And all of these things are written in a way that are modular, so you can nest them in a way that we have seen in the algorithm that was shown on the previous slide. And most of the constituent subroutines that we've implemented are ubiquitous across a variety of algorithms. And they've been written in a way as to be application agnostic as possible. And we'll see an example of that in a few slides' time. OK, so on the former, the quantum chemistry example is a good example of an algorithm that has gone from a big O scaling to precise resource estimates, in this case for computing molecular observables of quantum chemistry models. But that isn't the only thing that we've done in the last year or so. So just to give you a couple of highlights, we've also published a linear solver algorithm with world record efficiency. We've published the first explicitly compiled quantum algorithm for solving differential equations. And by closely coupling the algorithm design with the details of the architecture and error correction that sits underneath, we can drop the resource requirements for both RSA and elliptic curve cryptography significantly. So in fact, this paper outperforms previous resource estimates for this problem by about 2 orders of magnitude. Regarding compilation, I can give you an explicit example to demonstrate our approach. So this is a script that is invoking a ubiquitous subroutine known as a QROM, or a data lookup. Algorithms for us are instantiated using, well, a simple language that is just a wrapper on Python. And using the library that we saw on the previous slide, it's just instantiated with 2 lines of code, which you can possibly see at the bottom of the slide. And it's also instantiated in a way that's both largely agnostic about the constituent subroutines that make up that component, and also in a way that is agnostic about the data that is fed in. So that maximizes the modularity and reusability of the code. Compilation is handled by a filter pipeline that are arbitrarily composable and take a high-level quantum algorithm and successively break it down into lower and lower layers of abstraction until you get to some fundamental primitive set of gates that match your quantum architecture. And lastly, on resource estimation and optimization, this is a snapshot of the tools that we've built in this area. So I don't have time for a deep dive, but there are a few things that I'd like to highlight. So it's a little bit small, but it's worth saying that the graphical representation for quantum algorithms at this level is not a quantum circuit diagram. It is this topological object that you can see at the top that just retains the necessary information for carrying out resource estimation. And so each leaf in this diagram carries around a set of symbolic resource estimates. And then there is an engine that sits underneath that composes those symbolic resource estimates into resource estimates for constituent components and for the entire algorithm itself. So the prior art for this kind of bookkeeping is to do this process tediously by hand over many months. You then write a 90-page paper and you put it on the archive and you implore all of your colleagues to check whether it's correct or not. And clearly this approach is faster, it's much more transparent in how the algorithms are constructed, and it can be fed to automatic verification tools. Also, once the algorithm designer decides they want to plug in a particular problem instance for the resource estimates they're interested in, they can specify parameter values, and rather than getting just a top-line estimate of the total number of gates and qubits for the algorithm itself, you can get richer resource estimation information. So in particular, the output here is a cool graph with a heat map that demonstrates precisely where the quantum algorithm is bottlenecking in resources, which is precisely what you want to know if you want to iterate through new quantum algorithm designs. Okay, so to conclude, I hope this talk has given some insight into the progress that we've made in developing quantum applications and the tooling to support them. We are always willing to speak to both practitioners and end users of these tools. So if you are a quantum algorithms developer that wants to expedite your algorithm development process, or you're an end user that wants to marry these tools with a particular application, please come and speak to us. And then the last thing to say is that this has been primarily about algorithms and tools. If you want to know about applications more specifically, in this case in the context of quantum computing, our head of quantum solutions, Philip Ernst, will be hosting a discussion with Yannick Gamvros of QCware. So please scan the QR code or speak to either us or a representative from QCware if you're interested.
Do you have some time for questions if there are any questions?
You've talked about the large difference between NISQ and fault tolerance, and most of the talk you said how you estimate the resources for fault-tolerant computing.
That's right.
Did you also try to do any resource estimation for NISQ algorithms?
No, for a couple of reasons. One is that PsiQuantum doesn't plan on building any NISQ systems. That's the main one. But the other is that the framework relies on the algorithm lacking this kind of heuristic nature that you might expect for NISQ algorithms. So the precise reason why we can go through this resource estimation procedure is that even in advance of running the algorithm, I can be explicit about how long it takes to run, which is not something you get with a NISQ device. Thanks.
Exactly.